Today's topic is Runge Kutta method or RK method. This is the most commonly used methods to obtain greater accuracy and most suitable in case when computation of higher order derivatives is complicated. In single step method, we determine the function pi of x, y, h of x, y and h, which is the step length, depending on f of x, y and its derivatives, such that y of x plus h, this is equals to yx plus h into phi of x, y, h plus order of h to the power p plus 1. This is equation number 1. Now, if we put here p is equals to 2, then now from Taylor series, we have y of x plus h is equals to yx plus h into y dash x plus h square by factorial 2 into y double dash x plus h cube by factorial 3 into y triple dash x plus up to h to the power p by factorial p into y to the power px plus h to the power p plus 1 by factorial of p plus 1 y to the power p plus 1 x plus theta into h, where 0 less than theta less than 1. Now if we put p is equals to 2, then y of x plus h, this is equals to yx plus h into y dash x plus h square by factorial 2 into y double dash x plus h cube by factorial 3 into y triple dash of x plus theta into h, where 0 less than theta less than 1. So this is equation number 2. So from 1 and 2, we conclude that phi of x, y, h, this is equals to y dash x plus h by 2 into y double dash x, that is equals to f plus h by 2 into fx plus f into fy, as yx is equals to fx, as yx is equals to y dash x, that is dy by dx, this is equals to f of xy. So y double dash x, this is equals to, this is the function of two variable. First differentiate with respect to x, that means fx plus f into fy. Okay. So in two stage RK method, we said k1 is equals to h into function of xy, and k2 is equals to h into function of x plus alpha into h and y plus beta into k1, where k is equals to w1 k1 plus w2 k2. This is equation number 3 and this is 4. Now the constant alpha, beta, w1 and w2 are determined so that 3 agree with Taylor series of order as high as possible. So from 1 we get y of x plus h is equals to yx plus k plus order of h cube. And from 3 and 4 we get a plus h by 2 into fx plus f into fy, this is equals to w1 f of xy plus w2 into f of x plus alpha into h, y plus beta into k1 from 3 and 4. As f is equals to, we let here h into f of xy, so it is w1 into that is equals to w1 into f plus w2 into f plus alpha h f x plus beta into k1 into fy plus order of h square, that is equals to w1 plus w2 into f plus h into W2 alpha fx plus W2 beta f into fy plus order of h square, as k1 is equals to h into f. So k1 is equals to h into f. Okay, we put here, this is h into f. That means, which is true for all values of the constant alpha, beta, W1 and W2, and therefore for arbitrary if, thus we have W1 plus W2 is equals to 1 and W1 alpha plus W is equals to W2 beta. This is W1. Okay, W2 alpha. W1 alpha is equals to W2 beta is equals to half. So from here we get W1 is equals to W2 is equals to half and alpha is equals to beta is equals to 1. This is the possible solution. Thus k1 is equals to h of into f of xy and k2 is equals to h into f of x plus h y plus k1. That means k is equals to half of k1 plus k2, that is equals to h by 2 into f of xy plus f of x plus h y plus k1, that is h into f of xy. So y of x plus h, this is equals to yx plus k plus order of hq. Hence, the iterative formula is y of n plus 1 is equals to yn plus h by 2 into f of xn yn plus f of xn plus h yn plus h into f of xn yn, where n is equals to 0, 1, 2, dot dot dot. This is known as Runge Kutta method of order 2 with truncation error of order h cube. In similar way, the Runge method of order 4 can be written as y of n plus 1 is equals to yn plus 1 by 6 of k1 plus 2k2 plus 2k3 plus k4, where k1 is equals to h into f of xn yn, k2 is equals to h into f of xn plus h by 2 yn plus k1 by 2, and k3 is equals to h into f of xn plus h by 2 yn plus k2 by 2, and k4 is equals to h into f of xn plus h yn plus k3, where n is equals to 0, 1, 2 up to infinity. Here the truncation error is of order 5, h to the power 5. Now the advantage of this method is the method is stable and self-starting. It is easy to change the step size h for better accuracy. And for this method, several evaluation of first order derivative are required. So the method is time consuming, and the most disadvantage is neither the truncation error nor the estimates of them are obtained in the computation procedure.